right, so yeah, check out the midterm link up on here, has all of some of your midterms, very interesting stuff. So this is class 8. We've had a kind of a shift in what I'm calling the part materials because we went through part 5 for 2 classes. Last class, we went over part 6, which was a mostly kind of a practice with some data to help you figure out when you would want to pivot versus merge versus join and bind rows and everything. So we didn't finish that part. A lot of the stuff at the end was ggplot examples. And so I think I'm going to move on to part 7 because I want to cover lists and functions and other kind of iteration topics. And if we have time at the end, I'll go back to that part 6 and also maybe just incorporate some of those examples again. And so the feedback on part 6 was actually interesting to me because about half of you said that the topics we covered, pivoting, data cleaning, ggplots, was really unclear, and then half said clear. So I think that's just reflection of the fact that these topics are pretty hard and will definitely take practice. Sort of hard to throw all this stuff at you and just expect you to kind of either sink or swim in how to use it. So I think hopefully the homework this week let's do on Sunday will help a little bit with some practice. And then I think just I'll try to incorporate more examples as we go through the last few weeks of class. But it is hard stuff. So we're mostly going to leave data cleaning behind a little bit for the next couple of weeks because we're going to talk about iteration, but we'll bring it back a little bit more in the end when we talk about statistical modeling and summary tables and so on. Let me make sure I have my chat. All right. And so the other point was this use of .x. So when we use a cross and develop a function within a cross that we want to use for either summarizing or mutating, that is pretty confusing. And you'll see today when we talk about functions, what's really going on there. I think will become more clear once we talk about functions in general. Okay, then someone said that they tried to duplicate the merging of the mouse data by first pivoting and then joining or I guess binding. And I think that's possible, though doing the pivoting first, you have to make sure you're pivoting in the same way. And if you remember, there were some various issues with these time point data sets. There was like a column name misspecification typo. And so I think this kind of code would work. And you could do either. You could pivot and then bind them, or bind them and then pivot, whichever feels better to you. We're gonna work a little tiny bit with this kind of code in one of the challenges today. So hopefully if you have any questions about it, let me know. But maybe the person who wrote this could look at this code and see how it compares to what you were trying. There was a comment for new tools to provide a written explanation. That's a good point, and I will try to do that more in the comments of the RMD. And the other question was about the final. So I haven't finished thinking about what the final will look like. I'll try to do that by next week. I know we're running out of time, so I have to do it soon. I'm not entirely sure exactly what the structure will be. Last year, they did another project that was mostly based on machine learning and statistical modeling, but because we haven't really gotten to that, and I don't really like the idea of doing that because this isn't really a stats class, and I don't want people who have different stats backgrounds to be at a disadvantage there. So I'm still thinking on it, but I will let you know next week what I decide. Okay, so now we're on. Are any questions before I move to part 7? Okay. Let me look at my notes to make sure I haven't forgotten anything. Homework. Oh yeah. Yeah. So you have homework from last week that's due Sunday. I kind of shifted the due dates to be on Sunday because of the midterm messed everything up, but I kind of like keeping it like that because then I can have office hours on Friday and you get an extra weekend to work on it. And so hopefully that didn't cause too much confusion, but I don't have the homework for this week up yet. And again, I'll try to do that tomorrow, and then you'll have basically like a week and a couple days to work on it. Okay, so let me get out this thing. So this is part 7. And we are definitely shifting gears a bit today. We really got in the weeds with the data cleaning and everything reshaping and joining and all that stuff, which can get super complicated really quickly. But today we're going to talk about lists and functions and iteration, and some more about like automation. So this is going to be a bit more programming, less data cleaning, if you think about it like that. So this is technically part 7. I loaded in some data for you just because we use it later. There's a lot of data sets in here. I just sort of threw a bunch in to work with. But today, if we get through most of this, the goals are to really learn about what a list is and about its properties, how to get elements out of a list, some different properties and what a homogeneous versus heterogeneous list means. There's a package called purrr, which is a part of the tidyverse, and that has a lot of functions that help us with lists and also iterating over lists. So one of them is pluck. We're also going to talk a little bit about map, which we will go over a lot more next week as well. And we will talk about how to, actually, I forgot a big one, which is how to write a function. Maybe I should add that somewhere. Learn to write functions. That's what we're going to do first, actually. And then once we know how to write a function, we'll learn how to apply a function to a list and iterate over that list. So I will say that the first 2 sections will seem a bit disjointed because first we're going to talk about functions, how to create your own functions, how to use them for data visualization or wrangling or analyses or whatever you're trying to do. We won't touch on this too much, but we'll use that as we go along. And then we'll talk about lists separately, in a sense, and what that means. So a list is an object type in R. It can be very useful, as you'll see. And also we'll find out that data frames can actually behave like a list, even though they're data frames. And then we'll put that all together with something called functional programming tools. So R is a functional programming language, which means it has the ability to use functions and create functionals and use them in a variety of different ways, both iterating over objects like lists or vectors, or vectorizing functions. And so that in itself is very useful. Just the ability to create our functions and use them in many ways. And so one such programming tool is purrr map. And we'll use that to iterate a function over a list or over rows of a data frame. We'll talk more about this next time. And so in the R for Data Science textbook, there's a couple of chapters that are useful about this stuff that might help your understanding. So there's the functions chapter and the iteration chapter. And kind of a side note, if you remember, I think it was even the first class when we talked about for loops, that fits into this idea of iteration and automating our code. And I introduced for loops first because they're really fundamental building blocks of iterations. They fit nicely into this idea of computer programming. It's something that you do in many, many languages, not just R. But as R for Data Science textbook says, for loops are not as important in R as they are in other languages because R is a functional programming language. So this means that it's possible to wrap up for loops in a function and call that function instead of using the for loop directly. And so you'll see some examples of why it's just easier to use functions in general in R. It's also faster, which is kind of a back end thing that we won't talk too much about, but these methods like map are faster than doing a for loop. So functions, we've been using functions all along. For example, mean is a function, to upper. So they have arguments, we run them in R, they have a result or a value or an output. So the mean of 1 to 10 is 5.5. If we want to turn this string to an upper, use the function to upper, it creates this result that's a string, which is ABC in capitals. So this is kind of an inherent thing that we do in R. But what if we want to create our own functions, and why would we do that? So there's this kind of saying, don't repeat yourself, DRY, use functions. And the idea is that if you're doing something in R once and have to do it again, it's probably best to think of how to do it well once rather than cutting and pasting. So if you have an action or an algorithm or a series of data tasks that you're doing and you find that you need to do all of that over again, you might as well write a function and then apply that function twice or 3 times or however many times you need to do that. So for example, let's say you have multiple files on your computer and they have the same format and you want to load them all into R and then put them together into a single data set. So you can do this by writing a function to load in the data and clean it up the way you want. Because if you had, say, 10, 20 files, doing all those in code separately can lead to pain in your wrist. I don't know, it just takes a long time. You could have copy and paste errors. You could go wrong a lot of different ways. I think writing a function is just the most efficient way of doing that. And kind of the easiest way to debug and see where your code went wrong if you've only written that code once. So how do we define a function like in code? So for example, let's say we want to make a function and we want to call it square number. So like everything in R, it has a name, an object name. A function is really an object, a type of object in R. So square number is the name of our function. We use our assignment operator. We could also use an equal sign, but we've been just using the arrow for our assignment in this class. And the syntax is you write the word function, then you have a parentheses, and then you put something in the parentheses that defines or specifies your argument. So in this case, argument is named number. Square number is the name of our function. This is saying it has one argument and it's called number. And then you put the code of your function inside curly brackets. So this defines the beginning of your code block. You'll put stuff down below and then you'll close it with a end curly bracket. So let's write this function. Again, the name is square number. So I'll write function name. Oh, whoops. It's function name, assignment, function, argument name, and then curly brackets code that goes in there. So that's what the kind of typical syntax of a function looks like. So for this one, square number is a function that takes one argument, number, and what we do is we square it. So number times number is the square of number. Number we're assuming is a number, is essentially a vector of length 1 with numeric value. We save our results within the code block, output number, and then we return that. And so this return function inside the function is giving R, or telling R what you want the function output to be. So kind of obviously this takes a number and squares it. So if we run this and we invoke that function square number and put 4 in the middle in the argument part, you get 16. The other way to run this is to name our argument, just like we do with built-in functions, and we get 16. This return, you can kind of see yours might look different depending on your color scheme, but how it's like coloring function and return is a kind of clue that you're writing a function and everything is working well. So kind of look for that. And you'll see you can put a lot of different things in return. I will point out though that you don't actually need to use return. It does make things clearer because you're actually specifying what the output is. And once your functions get pretty complicated, and if you want to return multiple results or multiple, like a list of results, I would definitely use return. But if you're making a super simple function, the default output is the last line of code run. And so in this case, I took away the return. I didn't save it as output number here. It's just number times number. And so this will do the same exact thing without return. It just assumes you want to return that last bit of code run. But this can go a bit wrong, because if we have a function like this, square number again, then here, let me actually, so this is, if I run it, we see that it comes out with the number 16. Just to show you, let's look at the structure of that output. It's a numeric vector, length 1 of 16. But what if I add this bit? So I've saved number times number as my num squared. That's my function. If I run this, I see nothing has happened. So if I look at the structure of my output, oh, I run this whole thing. Let me call this. There we go. Oh, I guess it is. Well, that's actually unexpected. I thought it was going to say that it was null, so I might be wrong. But I think what's happening here is that it's saving it as the number. It's not printing it because we've saved it as something, but it's still outputting it, which is interesting. I actually thought it wouldn't output anything. So I learned something. But I think you wouldn't want to do this, because usually you want to both print. Well, it's not always true that you want to print your output, but usually you want to print your output, especially if you're just running it like this without saving it as anything. So it's something to be aware of. I would be careful when you're not using return. This is the preferred way of writing a function, is actually to specify your return. All right, so mini challenge. Take a minute and try and write your own function on your own. So we're making a function called cube number that returns the cube of a number, and test it out with an input, make sure it works. So I'll give you like a minute to start working on this. You might want to change this to true. Feel free to ask questions if you have any. Okay, so what we need to do is specify function. It turned purple. That's a good sign. I'll just call this num. And if you put a bracket, it tries to close your bracket for you. That's great. So usually I press a couple enters in there. And then I'm going to make my output called out num. And I'm going to say num to the third. So that's how you would cube a number. You could also do num times num times num if you want. And then I'll say return out num. Oops, don't do that. Run the whole thing. And then let's test it out. So I want to say cube number 100. So we get 1e to the 6, 2 is 8, and so on. If I did NA, what would happen? NA makes sense. And so simple functions, simple arguments, obviously can get really complicated really quickly. The next step up is the idea that you can actually add multiple arguments. So a lot of the functions we use in class so far take multiple arguments. And so this is a very simple one with simple argument names, just x and I. And what this does is it takes x minus the mean of x, so centers it, and then takes the absolute value and then raises it to the ith power. So looking at this function, since I want to take the mean of something, I can get a sense that x is wanting a vector. And since I'm taking something to the ith power, I'm going to guess that I is just going to be one number. So if I run this, and then I implement that function on the vector 1 to 10, and then 4, I can see that I've returned the results. And just like in other functions, you don't have to name your arguments if you are sure that you're putting them in the right order. So obviously that's the same thing, but if I did, if I tried to switch it, for example, you would get a different answer because it's just one number. The mean is, you've subtracted off the same thing, and then to the ith power, it's raised it 1 to the 10th power. So this is a vectorized function basically. And so what you've gotten is a vector, but you flipped the operations essentially. So it's kind of a silly thing to do. But this would have worked had I said I equals 4 and x equals 1 to 10. And so now it knows what you're trying to say. And it specifies those arguments that way. So these have been simple numeric functions. And we have here an example of kind of how do we manipulate text and strings. So this is a function that takes 2 arguments, name and pet, uses the function paste to put them together. So name and then apostrophe s and then pet, and then the separator of that pasting the string together is the empty string. And then I make that all capital letters. And so I can run this and I see it just creates a Jessica's cat in all caps. And like I said, you can switch the arguments, but you're gonna it's gonna assume that you put them in that order of name and pet. So it's good practice to specify your argument names just for clarity, though I admit I don't do that all the time. And so we've been running functions and just getting the output. Just like with regular built-in functions, you can save it as something else. So for instance, if I wanted to save it as the object pet string, run that function, get the output out, and then save it, I would see the same result. And now pet string is, if we look at the structure, a character vector of length 1. And so you can input that into other functions and manipulate it however you like. So just the same kind of result like we get from regular functions in R. So this is a string replace all. That's from the string R function, package, string R. And so I've replaced pet string, which was Jessica's cat, with every time I saw a cat, I replaced it with the dog. So that's what I did there. And up until now, we've just been creating functions with the names of the arguments right here. See how it says name and pet, but you can create default arguments, which means that if no one specifies the pet, this function will fill in mouse by default. So in this case, it's the same function, except I've just changed the default value of pet to be mouse. So if I run that, still I can override that default setting and tell it cat. But if I didn't specify that second argument, it would plug in mouse and made it capital. So it's capital mouse. All right, so here is a challenge to work on in your little groups. So I've noticed one of the muddy things that showed up again was if else being somewhat confusing, which I kind of agree. So maybe this will help trying to recreate the if else function. So the if else function takes 3 arguments. The first is a true false statement, like 1 equals 2, something like that. The second is the value to return if that statement is true. The third argument is the value to return if that statement is false. So here I'm asking you to just fill in some blanks. I've written the kind of structure of the function, and here we're going to use case when to try and replicate that if else function. And you can run some tests. You can compare it to the regular if else statement and see if you get the same thing. Maybe try some with NAs or numeric values or whatever, different tests, see if it works. So I'm going to stop recording. I'll just give you like 6 or 7 minutes to work on this. I knew I forgot something. Well, whoever is not here will not hear about the value of NA. Yeah, sorry. So the stuff that I did not record basically is saying that NA is a special case. It is not numeric nor character value. It's kind of its own value. R thinks that it's logical. But the flexible way to output NA, I would say in this case, is to make this little clause that first tests if my test value is NA, then just return NA. And so you can see I have two return statements. So it goes through this first. If it is not NA, then it keeps going. And then it doesn't return anything. So that's what this if statement does. And the if part, like the test for if, goes inside parentheses. So it's kind of like the syntax of a function where we have instead of function, we have if, and then we have the argument essentially, which is this test. And then we can put a code block inside the brackets, curly brackets. Let me hide this. So the next thing that we need to do is say what happens when my test is true. And so I put this, and then I said, if my test is true, then value if it's true. You maybe did something like this, which is fine, but this is sufficient because this is a true false statement. So case when you have a true or false on the left side and then the value on the right side. And so when this is true, then we put value if true. And then so the opposite of that is exclamation point, which negates that true false statement. I put it in parentheses. You don't really have to do that. And you can just leave it without parentheses. And then I put the value of false. And then I return output, which is what I was calling the output of the case one. So this is my function. I run it, so now it knows what it does. I use this test statement if 2 is less than 10. That is true. So we would expect it to be apple, which it is. And then if we just tried the regular if else, we'd see the same thing. Actually, I had a bunch of examples that I forgot thought I pasted them. They're down here. There you go. So I just kind of threw in a bunch of examples just so you can see. This is where characters, this is a similar idea. What if we say NA? Does that work? So if I've put NA in my test, it returns NA, which is good, which is what we wanted. Another true false statement might be is.NA, and then I input NA. This is true because NA is NA, obviously it's missing. And so I should expect a 1, and I do. Here I have my test statement is.NA 3. 3 is not NA, so that should be false. So I should expect 2. And then this is the if else version, which you get the same exact thing. Question says, could you similarly write the same function using if something else, if next case, else if last case instead of case one? Yes, that would do the exact same thing. And there is not really a reason that case one is better other than I already taught it to you. And I think I use it a lot in data cleaning and data wrangling. I also just like the format because you can see them all lined up. But that is what case one is doing. It's saying if this, then result in that, else if this, then result in that, and then we could add another one, else if this, then result in that, and you could keep going. There's also a base R function called switch, which is like switching through cases, which does something similar that I used to use before someone invented case one. But now I just tend to use case one because it's, to me, the most clear and easy to write version. But yeah, that's a great question. Yeah, because if there's also, you'd have to write it like this, else if this would be otherwise do this. And often actually, it's actually, I think, computationally more efficient to put it inside, put that code in. No, I just tried to fix my indentation, didn't really work. To put it inside the else if statement, because it's like slightly computationally advantageous because it checks the if or the else if. And so I guess that's a little bit faster, but obviously we don't really care about that. It's going to be fast no matter what in this case. But just so you know, this is another kind of else then type function that's built into R. And you can see it changed to purple because it's also kind of one of these special logical functions. But yeah, I tend to use case one for most things. Other questions? Okay. One thing I want to show you that maybe you haven't discovered yet. What if we just type the word if else in the console? So this is an interesting thing of R. It's open source. A lot of the functions are, well, all the functions, if you know how to find them, are available. If it's a kind of relatively simple function and you type its name in R, you'll actually be able to see the code that writes the function. So obviously this is doing a lot more kind of testing. It's checking if it's null. I didn't even think to do that. And there's like a lot of other stuff it's checking. Then it uses some code to test the test. And so there's a lot of stuff going on behind the scenes in if else actually. And so what happens is that R saves that code and it outputs it if you call it. If you say something like mutate, for example, it's not going to show you the extremely complicated mutate code probably. It's just you have to actually go into like GitHub or the actual R package files to find the code, but it's all available somewhere. So if we use, I just lost my name. So if we did that with the function we just created, you can see that it outputs the code that we wrote to square our number. And even if you put it in here, it will, in your code chunk, will do the same thing. So the function is a function and it's all written in there. And so those were relatively simple functions. The if else thing was getting a little more complicated. Usually I'd say for data cleaning or manipulation, a lot of times you are doing a bit more inside your function. Like you usually don't bother to write a function for something that's super simple, but if you have a lot of steps that you're trying to recreate, that's often when I write functions. So this is an example of a little bit more complex operations. So this function is called load underscore files, and it takes an argument path, and path is just a string that specifies the file location or the directory and file name, file path of a file I want to load in. It's going to be an Excel file because I'm using read underscore Excel. And I know that I just want to read the first sheet. I also know that I want to clean the names, and then I add a column called source, which is actually the argument path. And then I return that resulting data frame. So inside the subfolder data, there's one of the smoking data sets that I think we've read in before, I think in the homework. And so we're reading in that file, and then we're cleaning the names, adding a column, and we're returning it. So we'll run all this. And so we've saved it as smoke one, and then I've called smoke one. And so we can look at it, if we go all the way to the end, we can see that now there's a column called source, and that has that argument name. When you mutate and name a column and then just give it one value, it gives the whole data set that value, just so you know. So that's why there's this same thing for all the rows you can see. And we'll use this function a little bit later as well. So kind of an aside, we talked a lot about across within summarize, within mutate, and we made some functions. But another way to do that is to actually make your own function and call it something, and then invoke that function in across. So let's make one which standardizes a vector. So the function is called standardize fun, and then the argument is vec, which is just a vector, a numeric vector we'd expect. In this case, we subtract off the mean of that vector, divide by the standard deviation of that vector. We call it vec2, and then we return vec2. And so this function has a name. We've called it standardize fun. And so now when we use across, we specify the columns. Let's specify the numeric columns. I'm going to mutate all of the numeric columns in the same way. And then I'm going to standardize fun on those columns. There's actually only one numeric column in this case, so it's a little silly to use across, but this is how we would use it. We would just call the function, just like we did with mean or not mean would be summarized, but any kind of function that was already built in R, we just call it by its name. We don't add parentheses, just the name. And so we can see age diagnosis now is no longer in like large numbers of days. It's a standardized value. So just so you can compare to what we've been doing, we have done things like this, but we've built the function inside the cross. So I admit this is a clunky kind of way to do this, but it does the exact same thing. So instead of vec, now I have this .x because that is the standard way to specify the argument of this like new custom function. I've subtracted off the mean and I've divided by the standard error, and I put a little tilde in front to specify to R that I'm starting a function now. Pay attention. And so it's the same idea, except it's a little bit, I think it's a little more clear to create your own function and then just call its name. But you can see where that .x idea comes from. It's instead of vec, R expects you to call your argument .x. For a while, I was using dot because that was an old style way of calling an argument, but I think now it's pretty standard to use .x, at least in the newer examples I've seen. And so you might also think of a function the same as the standardized func up here, where I saved it as vec and vec2 and use the argument vec. This, what it's really doing here is the exact same thing, except now I've just called this argument .x, .x, .x is everywhere. So same idea, taking an argument, doing some mutation on it, and then running it. So you can see we get the same thing, agic diagnosis. And the same idea goes for summarize. So that was mutate across, and we specified our function. If we want to do that with summarize across, we'd want to create a function that creates a summary value, right? So this function manipulated a vector and returned a vector. So the input was a vector and the result was a vector. The summarize function needs to take a vector and then output just one value. So in this case, I took the mean of the vector and then divided by the standard deviation of the vector. So it's just going to give you one number, basically comparing the mean to the standard deviation, kind of like an effect size, or standardized in that way. And so just to show you how we would use that in summarize without a cross, we would just use that function and invoke it inside summarize, just like we would any other function, and then set what column we wanted to use. So this is the penguins data. I'm going to run this function, and then I'm going to run this line. And so we can see this was the output, mean over SD of bill length, and I grouped by species, so I got 3 results. We can also use across. In this case, we're doing the summarizing function over every column that is numeric, applying that same function. So we got bill length, but we also got bill depth, etc., even year. So a lot of flexibility with functions. You could really do whatever you like. Though, if you looked at, when we looked at if else, you can see that there's a lot more going on. There's a lot of testing that goes on, and that is mainly because to write a good function, you usually want to think of every possible case that someone could input. So if your function is supposed to only take character vectors and someone tries to put in a numeric vector, it's up to you, but I think good practice is to test whether that input is numeric or character, and then tell the user you're not supposed to input a numeric vector. give some kind of error or maybe a warning if that's appropriate. That is informative, though obviously working in R for a while now, you've realized that not all errors are actually informative. But what happens if we do square this number? So square number is going to take a number by default, that's what we would hope. But if we put in a character, we get error, we get an automatic error that's just from R that says error, non-numeric argument to a binary operator. That's a very common error that I get a lot. Maybe you do. Doesn't really tell me much, except that something's non-numeric. So that's a clue, but we can actually build in a test that says, what if we don't give a numeric value? I don't want to like go through the process of trying to square it. I'm just going to tell my user that that was wrong. So we're going to use an if statement again. So if statements check for a condition within the parentheses inside here, and then execute code in the curly brackets if that's true. So if we add this if statement above the place where we put the squaring code, and I'm testing whether the input, which is called numeric, so that's the argument name, it's called number, sorry, the argument is called number. I'm testing whether it is numeric. So is.numeric is giving a true false value. So if a number is numeric, I'll get a true. If a number is a character, I'll get a false. And that means if not, we want the opposite, because we want it, if it is not numeric, to give an error. So if you don't get a true statement, that means if you get a false statement, then you will say, stop, this is the error I want to give, your input was not a number. And then if we pass this test, if the number is numeric, then we do the squaring and we return it. So if we run this, which saves my new function as square number improved, it works well for 2, but if I say 2, I still get an error, but it's a little bit more informative. So it says error in that function, your input was not a number, which is what I told it to say. And just notice there's this trace back. This isn't really that long, but sometimes you'll get this and you'll click on the show trace back and it's like has like 20 lines. Usually you want to look at the last thing that happened, which is going to be the top line, but sometimes you can dig a little deeper to kind of help you debug where something went wrong, just so you know. Sometimes this traceback is useful, sometimes it's not. In this case, it's really simple, so there's not really much to see here, but I can see the place where I got my error. Any questions about errors? I will say that most of the time I don't, if I'm just writing a quick function for myself, I won't write in things like this to check for errors. If you're writing a function for other people or for like a group of people, like your lab or collaborators, it depends on what they know about your code or what they know about the function. Also kind of depends like how well you document your code. So some things might not be obvious that you're anticipating. So you don't really need to check for all errors, but it's good practice to check for some of the trickier ones. Or if you're releasing your software, like if you're making a package and you're putting it up on GitHub or wherever and you're sharing it with the world, it is a good practice then to really think about doing more extensive error testing, especially the functions that will be used the most. Otherwise, people will get quickly frustrated and not use your code, which you don't want. So when should you write a function? We already kind of mentioned that if you're writing something, some code, and you're doing it many times and you're copying and pasting it probably at least 3 times, you should think of writing a function. So you can, there's some advantages over copying and paste. You can give the function a name that makes it easier to understand. If you decide you want to do something slightly differently, you only need to update code in one place instead of many. That I think is really the key. If you realize, oh, I actually wanted to add this step, you only have to do that once. And of course, you also eliminate the chance of making incidental mistakes when you copy and paste. So saying the wrong variable name, forgetting to update like the number, like if you're doing it with data 1, data 2, data 3, and then maybe you accidentally made the second one data 2 twice. That happens to me all the time. Copying and paste errors is a easy thing to break. Okay, so here is another function that takes a data frame that up until now we've only used arguments that are like vectors or text, or so we can, and we'll see this next week when we start working a little bit more with functions and data frames. We can input a whole data frame. In this case, we're calling it df. Count categories is the name of the function, and then we're actually just counting disease. So we're using the count function. This is super simple, counting how many diseases there are. And we're going to return that data frame. So that's the function, and then I'm going to invoke it on some of these data. So smoke complete, we can see, has counted up all the different disease categories in that data. LUSC data only has that one kind of disease, and the SO only the one kind of disease. But what about if we do that with another data set? Lots of errors. And why is that? Because if we look at penguins, what are the names of penguins? There's no disease in there. Should I say call names? The column names, there's no disease. So this idea that we are counting some column, we're really assuming that we're using this in a very specific way. Disease is what we would call like hard coded to use that column name. Probably we would want to include a function argument that tells us what column we want to count. And we'll talk about how to do that later because it is a little bit complicated. Because if you notice, this is not a string value. This is not, it's the name of a column. There's no quotes. And so there's something called tidy eval, which we haven't really talked about yet. And we'll talk about maybe next class and how to make functions using tidyverse functions, tidyverse verbs and functions and column names and so on. Okay, so another challenge. This is the idea that you don't want to repeat it yourself. So what I've done is I've kind of basically from last time, we'd had the 3 mouse time point data sets, right? We read them in, this is how we read them in. I've just copied all the code, but we did it 3 times. So we read in 3 data sets, pretty much the same way. Then we changed the column names. And this is something that we could have done to all 3 data sets, but we didn't need to. And then we did some renaming and filtering out data that was missing for the ID value. And then we made these numeric for the preference outcomes. And we did that for every, we can do that for every data set basically. And then we pivoted the data. And so this kind of is going along with that muddy point about pivoting and then binding. So that's what we're doing here. We're pivoting each data set and then we want to bind the rows. So what I want you to do in your challenge is to take this code and don't repeat yourself. Make a function that does all this stuff. It's really just rearranging the code and making it more general and putting it inside a function. So your function should load in the time point data from Excel, clean the data like we have here, just use the exact same code, name the columns like we did below, and then pivot the data like we did below. The function should have 2 arguments, which is the name of the Excel file, so basically what goes here, and the name of the sheet or the sheet number, either one. Yeah, it shouldn't be the name, it should be the sheet number. It's a little easier, sheet number. And the function should return the like pivoted data set. So individual mouse 10.1 pivoted data set or 10.2 or whatever. And then after you run the function 3 times, you'll have the sets that you can then bind together. And then if you have time, add an error check to see if the sheet number is not between 2 and 4, because you only have those 3 sheets to read, and return an error to say something like, that's not time point data. And so I'll give you 4:30, yeah, like 10 minutes. Come back at 4:38 and I will pause my controls, pause. Like seeing all your faces. Okay. Hopefully you got decently far in this. I will just I'll do the reshaping of the code in front of you just so you can see my thought process. Okay, so the first thing I want to do is just make one example with one data set. So I'm just going to do this with mouse TP1. In this situation where that one data set had some random junk at the bottom and we needed to specify n max, because these all have the same number of IDs, we actually can leave that. And that can be generalized for all the data. And the column name situation, same thing. We only had to change the column names for mouse TP2 because there was a typo where they said NG when it should have been PG. But I'm going to do that with all of them. So I'm just writing, actually, I'm just going to call this mouse TP because that's a little more general. So I'm changing every time I see mouse TP1 to mouse TP. And I'm going to rename, filter, and mutate on one data frame. I don't need this other stuff. And then I'm going to pivot the data. And I'm going to call that mouse TP, mouse TP. And so this is everything that's going to go on my function. So I'm going to put, actually, I'm just going to run this to make sure it works first, probably. And it's all green. That looks good. So I'm going to write my function. So I forgot what I called it. Pivot, load, and pivot function. The argument is going to be, first I said I need the name. So I'm going to call that path. And then I'm going to call sheet num my argument for the sheet number. And I put a bracket, and then I put a bracket down at the end. And I'm going to bind this later, so get rid of that. One shortcut I like in our studio is, for me, it's Command-Shift-A, which kind of re-indents my code and add spaces and stuff to make it a little more readable. I do that just because I like, I mean, it's kind of a little bit more readable if you're indented inside your function. We haven't talked really about like nice code and kind of a style guide for code. Maybe I'll put up in a next class or a couple classes from now. But there are kind of standardized ways of writing code. And I think having indentations after a function or a for loop or whatever is kind of a standard thing to do. So I do need to specify my arguments. This is my path. And then this is my sheet num. So I'm going to run that function, and then I'm going to test it on, I shouldn't have removed, what was it called? Path equals mouse biomarkers XLSX, maybe? Sheet num equals 2. Nope, what's it called? It's way down here somewhere. It's just biomarker. Okay, there we go. So I forgot, I can see I ran it and nothing happened. And that is because I forgot to return my output. So I want to return that final data set. So I'll run that function definition again, and I'll rerun my invocation of that function. And I can see I have a long data set that has biomarker type, biomarker value. So these were column names at one point, and these were the values under those column names, but we've pivoted it to be a long format, which means the column names turned into the categories of this column, and the values turned into one long value vector. And then everything else got duplicated. So SID 137 now has these, whatever, 7 rows or whatever it is. And their other values got duplicated because they weren't specified in the pivot. So we have 3 time points. So what I want to do is now call mouse time point 1, the result from here. And then mouse time point 2, mouse time point 3, and then this was sheet 3, and this was sheet 4. So run them all again. And now this should work. If I bind them and call it mouse TP and see that it has, well, it's sort of hard to see. Let's just view it. You can see if we scroll down, eventually we get time point 2. I'm looking at the time column, and down here is going to be time point 3. All right. The other issue was, if you have time, add in an error check to see if the sheet number is not between 2 and 4. So we could add this at the top here. If sheet num is less than 2 or sheet num is greater than 4, stop incorrect sheet num value for time point data. Okay, so let's see. If I run that, I've redefined my function. Oops, see, that's why I don't use view and here. So if I redefine my function, these all should still work. So I would still test those, yes. I would also just kind of test this out to make sure my function error didn't work. So if I put a 5 here, I get a red that's telling me there was an error in the load and pivot function, incorrect sheet num value for time point data, exactly what I told it to say. So that's good. Looks like that's working. Like if you remember, the demographic data was sheet number 1. And so we get the same error, and we don't want to read that in the same way because the pivoting wouldn't work and all that stuff. All right, any questions about that? I didn't put it here, but that's up there now. All right, so next topic, like an hour and a half left. What are lists? So switching gears again, we're going to talk about the object type in R, which is called the list. And so lists are, we can think of as a general purpose data structure in R. It is what it sounds like, a list of things, any kind of things. They are flexible in that we have slots. I call it elements a lot, like the first element, second element, third element, but we can think of them more as like slots that we fill in. And a slot can contain anything. It could contain a vector, a data frame, or even another list. Or like it could even contain a function or anything, any kind of object in R, really, is what you can put inside a list. And so the idea for like using lists in R, just talking simply, this is how you specify a list. Use the function list. We saw this briefly in a previous class. And then oftentimes you name the elements of the list, but you do not have to do that. So here we have a list that has 3 slots or 3 elements. We're taking character vectors. The first character vector has length 2. This one is just 1, and this one is 2. Cat name, hedgehog name, dog names. So if we run this my list, and then we call it my list, the output, then we can see this is how R prints a list. It gives you $, name of the element or slot, and then prints out the insides kind of. And so there's a lot of functions to work with lists that tell you the properties about it. So for instance, this is the same list. If we ask for its length, then we should get 3 because it has 3 slots or 3 elements. And also because we've named the list, if we ask for its names, it will give us cat names, hedgehog names, dog names. So that's a character vector of length 3. The thing that is kind of unusual that takes a little bit of getting used to is how you actually ask R to pull out one of those elements. So the first thing you can do is, if it's named, is use the $. I've shown you $sign with data frames kind of briefly, but we don't use it that often in the tidyverse land. But if we did the same thing with lists, we would end up with that first vector. And we can see the structure of that is a character vector of length 2, 1 to 2. The other way to access that first element is to use double brackets. So this is a very particular list kind of thing. List syntax, I guess, that's the accessor for the first element. And we would run that and we would get the same thing, an vector, character vector of length 2. So the double brackets specify that you want that first element. You can use the number, so that's the first one, or you could use the names and you'd put the names in quotes. So this is calling the pulling out that second element by calling by the names. And if we look at the structure of that, that again is a character 1 value. For dog names, again, we get the last slot, which is that 2 length character. And so I could have used the $sign there as well and gotten the same thing. Though I'm using double brackets, you should realize that you can use single brackets, but you're going to get something else, some other kind of output. So for example, this is just the same list over and over so you can see it. If I use single brackets on hedgehog names, what does that look like? Now we have this extra $sign hedgehog names above result. And that's because it has created a list of 1. So when you use double brackets, you've pulled out the actual true element, which is a vector. If you use a single bracket, just 1 bracket on either side of the name, you end up with a list. So it's like a sub list, I guess. So similarly, like if you did dog names with just 1 bracket, you get a list of 1, which is called dog names, and it has the vector inside of it. You could do something like my list 1 to 2. Let's say 1 to 2. And now you have a sub list that's 2 elements or 2 slots, and you have the first 2 slots. So just be careful when you're pulling out elements and look at what your result is. In most cases, if you're just pulling out 1 thing from a list, 1 slot or 1 element, I would use the double brackets because that's going to give you kind of what you expect it to be, like down to its true element type, a vector or a function or a data frame, whatever's inside that element or slot. So what does this do? This is like double bracket and then a single bracket. That has taken the first element, which was Morris Julia, and returned the first element of Morris. So this was a vector. So if you remember, if I just wrote out this vector like this and called it my vector, whatever, and then I used single brackets on that, I would get the first element. So that's what that's doing. It's taking that list's first element, turning it into the result, which is this vector, and then taking the first element, Morris. So I mean, I would say I don't use this kind of syntax that often. I'm not often pulling out bits and pieces of my list. Usually just picking it out like the first slot or the second slot. I'm not often digging down in there, but it can be useful. We'll see some examples later just to know how to do that. And so if you look at the structure of that result, the 1, 1, it's a character value of just length 1. Though this can get a little weird. So if you try to pull out something that doesn't exist, so remember this is just 2 names, Morris, Julia, I guess. And I tried to pick out the third element of that, you get NA. Okay, that kind of makes sense. It's missing, it's not there. There wasn't one to begin with. If I try to pull out the 6th element of my list, but it only has 3 elements in it or 3 slots, then we get an error, subscript out of bounds. So this is the subscript that's out of bounds. If I try to pull out the name of something and I spell it wrong, here I put 2 G's instead of 1 G, I get null. So be really careful when you're coding, hard coding like element names or slots or numbers or whatever, because you could get a strange result that is unexpected. just so you know. So mini challenge, just think about this on your own. Here we want to find the length of the cat names element in my list. So how would we do that? So first thing we need to do is pull out cat names element or slot, and then we want to take the length of that. So I would say length, my list, for instance, 1, and I get a 2. I could have also have put the name with a $sign if I wanted, cat names, 2. So if I had done this double brackets, but I only put 1 bracket, the length of that is going to be 1, because that's telling me it's a list of length 1. Because if you remember, if I use a single bracket, I get a length 1 list, which is cat names. So if I look at the structure, list of length 1. So that's why if we say, what's the length of my list? 1 without 2 brackets, I get 1. What we really want is this one, the list of that vector inside the first slot. There's actually a tidyverse way to pull out elements of a list, and that is to use a function inside purrr, which is called pluck. So you're plucking out one slot or element of our list. So same list, and I want to pluck cat names. It's kind of like using the $sign, basically, in a tidyverse way. So I use the pipe, my list pipe pluck cat names, and I end up with that vector again, and I can look at the structure, and again, it's a character vector length 2. Okay, so we haven't really talked about data frames. We will in a little bit, but data frames are list-like. So what happens if we used pluck on species? We actually end up with this long output, which is telling me it's a vector because it doesn't look like a data frame output. And it has levels, so that means it's a factor. So if I looked at the structure of this thing, I would get a factor with levels. So it's a factor vector. So the question is, did it return a data frame or a vector? It returned a vector that has type factor. But what if we did that typo that I had up above inside pluck? Again, we would get null. So it's the same kind of reaction if we try and pull out something that doesn't exist. And another nice thing about lists is that they're really flexible in the sense that they're not fixed length. We can take an already made list and add a new slot to it by using the $sign or not the, well, different ways, but by using the assignment operator. So this is our original list again with the names. If I want to add a slot called raccoon names that just has one name, Rocky, and I would specify that name after the $sign, assign that to, or assign the vector of length 1, Rocky, to that name. So if we look at my list now, we can see it has length 4. It has the 4th slot now, raccoon names. I can add also another one, and I've added cat ages in my list. So now we see actually I've added numeric data. So these are all character vectors. Now I've just gone and added a numeric vector. That's totally allowed. Lists can take any kind of data, and they don't need to be the same type. So it's kind of like adding a column to a data frame. You can keep adding columns as long as you like. Maybe you want to use mutate, or you can actually use the $sign in the same way. Like if I said penguins, new column is 1. I've just added a column of all 1s to penguins, same idea. Here it is. But lists are very flexible like that. We could also do that. So this is using the names, adding things by name, raccoon names, cat ages, whatever. But we could also do that numerically in terms of calling out the number of the slot. So here's a different list, finally mixing it up. One thing I want to note is that this time we have a mixture of named and unnamed, like nameless slots, right? This first slot is hello. second slot has no name, third slot is stuff. If we look at the output, we can see R didn't know what to call that, so it just called it 2, but it did call these things by its name. And if we look at the names, we end up with a character string where the second one is empty, just an empty thing. And so if I want to add the fourth element, and I don't want to name it, I just want to put in some new stuff vector. And I look at that list. Now I have 4 elements. The last one is not named, it's a vector, as I specified. What if I add the 6th element now? Does that work? What happened? So I've run that. I now see there are 6 elements, and the 6th element is exactly what I wanted it to be. But because there was only 4 before, it added this kind of empty, null 5th element. So it forced that to exist. And if we look at the names again, the only 2 elements here named are the first one and the third one. So you can do a lot kind of magic stuff with lists like this. And so you'll see why that's useful when we start running functions on them. But just a note, so in this idea that you can put whatever you want in a list. So a homogeneous list would be something that a list that has maybe all numeric vectors or all data frames or whatever. And so often we're usually assuming that our list is a homogeneous list when we're automating a repetitive process, so applying a function on every element of a list in the same exact way. We're probably assuming it's all like they're all numeric vectors or they're all data frames. But it's not always true that lists are the same type. They can also be heterogeneous, as we saw up here where I was adding, up here I added numeric values and then there were some character values. So they can be really flexible. And it's actually, you've probably seen these type of lists before. So if you've taken any stats classes that used R and you've run, for example, a linear regression model using just the regular R function LM. If you haven't seen this before, LM runs least squares linear regression, where you specify the outcome here on the left side of this tilde. And on the right side of the tilde, you put your predictors or your covariates. In this case, we just have 1. And then you also have to tell what your data frame is called. And then you can specify, I'm saving that as output. And then summary is a function that we often run on models to get out like the coefficient estimates and the variances and the p-values and all that extra information that we need. So I'm running this, I'm running the model, then I'm running the summary. And so what is some output? If I just print it, we can see it has a printing kind of defaulting that specifies what it's showing you in the output window. It's giving you the coefficients, the call, residuals and stuff. But what it really is, if we actually look at that object, and let's look at the structure first, actually, it's a list of length 12. It has a lot of things in it: call, terms, residuals, coefficients, alias, sigma, et cetera, et cetera, et cetera. Just looking at the names of that list, these are all the element names. And we can access any of those elements in the ways I showed you with the double brackets, with the $sign. Here I want to pull out the coefficients, and that pulls out that slot. You could also have used double brackets for coefficients. And so we can just pull out that. So don't assume that just because you run it and you look at the output and you see this stuff, that is all that's in there. Often for these type of functions, they are returning a list of a lot of things that you can pull out and get, and then kind of deal with in different ways. So for example, a function that we might write that returns a list and returns a heterogeneous list would be an example here. This is kind of a contrived example because we're doing essentially the same thing as running a linear model, but in this case, it's a function that is that linear model, the same one we did just above, but on a subset of the penguins. So the argument is my island. So you would pick one of the islands that's in the data set, filter the data to only have penguins from that island, that same model, get the summary out, And then I would create a list of the things I want to return from that function. So I'm going to write this a little differently. This is a list of 3 elements called coefficients, call, and island. Coefficients I pulled out from the summary. Call I pulled out from the summary. And then island is the argument that I input just so I can keep track of it. So this is my custom function, and then I return that out list. So let's run that function. It's defining it. And then I'm going to run that function, run penguin model. My argument is Torgensen. I'm just using this same default island output model. And then let's look at the output. We can see this list, coefficients, the call, which is just the call of the linear regression model, the specified arguments and everything. And then the island is a character vector of length 1. And so I could pull out elements from that. So this is, I'm doing all your mini challenges for you, but the idea here is that you would, and R actually tries to help you. So I want to pull out something. I know it has 3 arguments. That's what R is telling me. This is telling me this is it's actually a matrix, but it's like a table, basically, either a data frame or a matrix. And this is telling me it's something else. Call is something else. And then island is a character. So let's pull out island, and let's pull out, oh, let's do that, call. And so we can pull out arguments that way. I could also have done, oops, 2, same way, or 1 gets our coefficients. So we've resulted in a list from that function output, and we can use same way we use lists. So I would just sort of, as an aside, was telling you that this here is what's called a matrix. I don't know that I really mentioned that that's a data type in R. It's different slightly from a data frame in that everything in the matrix has to be numeric. I don't know why Summary decided to output a numeric matrix. It's very old school R, so I guess that's probably why. There are a few functions in R that only take matrices. And so you can usually turn, well, you can always turn a matrix into a data frame or a tibble. You can turn data frames into a matrix if everything is numeric, just as a heads up, if you ever run across a function that takes a matrix. So just looking at the structure of this thing, num1214, that tells me it's a matrix, not a data frame. It still has row names and column names, which is allowed. You can have named vectors and named matrices and so on. I used the function as underscore tibble, which turns that into a tibble data frame. And then I used GT on it. So if we want to see just a slightly nicer table, you can do that. And I've also used this like a data frame. If I want to get rid of T value, maybe I don't want to show that, I could run that. And now it's just those 3 columns. So just, I wanted to just show you what a matrix was, because it might come up if you're ever dealing with, like, say, correlations of big data sets and things like that. Some of those functions do require matrices. All right. Another, any questions? Checking. Another thing I vaguely mentioned early up is that lists can be anything, even lists of lists. You can have a list inside a list, which gets confusing quickly, but it is possible. So this is an example of that. Here we have a list of length 3. They're all named. The first one is the person's name, pets, and then address is a list that has 4 elements. And it's a little bit heterogeneous in that one of them is a number, the rest are characters. And so if I run that and look at that list, I can see the printing is a little odd. It's trying to tell me that this is a list inside of a list. So you get address, number, address, $, street, city, state, etc. And we can do this double brackets to pull out, let's say I want the street element I would use double brackets to first pull out the address slot from the original list. That is a list. I can see a list 4. And then I'd pull out the street element using double brackets again. And now I'm resulting in this character vector of list 1, length 1, just this one street name. Another side note, what happens if we use view on a list? It's kind of interesting. If I ran view on, let's say, my info list, for example, we've run view on data frames and we can see the data frame nicely, and I kind of explore it and search it. Same idea with the list, though it's a little clunkier, but it does show you what's in there. It gives you the type, which is handy. So this is really handy if you have a long output list. So for example, what was it called? Output. If I look at the output from my summary object, the linear regression, there were list of length 13. We can look at coefficients, fitted values, model, all kinds of things. You can kind of see the type, like I was saying, the call is another odd variable type language. And there's also this stuff over here. If I can click on, let's say, where did coefficients go? Let's do coefficients. If I click on that, it writes the code for me to pull that element out, which is handy. Because if I wanted to get, let's say, here's a better example. Terms, let's just do one of these. If I want to get something within a list of a list, you can see I wanted model, then body, mass G, and it gave me the code to pull that bit out over there, which is a 342 length integer. So this can be useful. I don't use it that often, but if you're really trying to look at something, because if you print this out in the console, or not that one, but if you print out, let's say, output in the console, it actually gives you the print statement and not the actual list value. Structure gives you kind of a mess to look at. So I think view is a little bit easier to look at. Similar information, but more friendly, user friendly, I guess. I lost, where am I? View, okay. So data frames are not exactly lists, but they are list-like, and they have a lot of list behaviors. So you might know just from like a couple examples that you can access column names in a data frame or a tibble using the $sign. And that is because data is kind of a special instance of a list. It's like a list with restrictions. So you can use all of those same kind of functions and accessors with the double bracket. So let's just use empty cars. I don't know why it's kind of silly to use empty cars, but bringing in another data set. So what is empty cars? It's a data set with cars. We use this a couple times. So these are the column names. If we wanted to say, what is the length of empty cars? What does that even tell us? It's actually telling us the number of columns. So if you think of a data frame as kind of like a list, the columns are the elements or the slots in our list. And so they do all need to be the same length. That is the kind of restriction around the data frame because you want it to be a rectangle. And so again, we can use $sign to pull out one of those columns, in this case MPG, and we get what's inside that element or slot, which is a vector of length, however many number of rows it had. And so if we just pull it out using the number, you get the same thing. And we look at the structure, it's a numeric vector, length 32, that was the number of rows. And I could have also used the double brackets in the same way. But I mentioned the difference between double brackets and single bracket. So for a list, when you use double brackets, you pull out that slot and the type is whatever was in that list slot. So in this case, a vector. If we use a single bracket on a list, we end up with a list of length 1. But in this case, you can see it actually made a data frame of length 1 or columns 1. When we look at that structure, it is telling me that's a data frame, 1 variable, so one element, 1 column, MPG. We just took the first one. So be careful when you're using brackets on data frames too, because you're getting something a little bit different than if you had used double brackets or a $sign or whatever. But we tend to just use select because we're doing tidyverse work. One thing, just so you know, if you ever see something like this, a way to filter data, which was the way we all did it before tidyverse existed, is to do the filtering code inside inside the bracket. So empty cars is a data frame. So that means when you use, let's say, empty cars 1, 2, that's giving me the first row, second column, and that's a 6, whatever that was. If I want to specify rows to pull out, the true false vector essentially in that row slot. So this is a really clunky kind of way of writing code, I think, because you have to first specify the data frame, then you specify your filtering essentially statement. In this case, I'm saying when the cylinder number is double equal to 8, and then all columns. So I'll just show you what this does. We can see that now CYL cylinder is only 8, and we have all the same number of columns. And what this is really doing is what we've done in the tidyverse filter, where the column named Sil is equal to 8. And so just in case you ever see this kind of code, you probably will see it, especially if you're taking stats classes and your professor doesn't use tidyverse, you're going to see stuff like this. And that's how you would do filtering, or you could do selecting in the same way. But this can get complicated really quickly. So this is how you would use brackets and $signs to do one tidyverse operation that we do this way. Okay, so we have like almost an hour left. The last topic that I want to start today and then keep talking about next week is this idea of iteration. Doing the same thing over and over and over again. We saw for loops on day 1. We practiced them to iterate over vectors. We can also use a for list to iterate over, a for loop to iterate over a list. So let's take our names and ages of our pets list. And so if you remember, the for loop is you say for, and you call your index, whatever you want. In this case, I'm just calling it index in, and then whatever you're looping over. In this case, I'm looping over my list, a list. Then I print, I'm just going to print the length of that index. So I'm going to print the length of cat names, which is 2. I'm going to print the length of hedgehog names, which is 1. I'm going to print this length, which is 3. And then I'm going to print this length, which is 2. So here, that's exactly what happens. 2, 1, 3, 2. If I just want to print the first element of that list, I would just call the index and then pull out the first element. So here, I've gotten just the first element of the first slot, then spiny, then rover, and 10. So it's pulled out that first element from each slot. So I've iterated over the list. And so we can see that for loops can be useful, though they have their pros and cons. Pros being that it's a classic programming approach. For loops are common in all languages, really. Pretty easy to understand because you can see exactly what's happening. You write out the code in the order that it happens, and it's kind of a little bit easier to write in that way, I'd say. It's easier to adapt because you can just keep adding stuff to your for loop, and kind of easy to debug. I haven't really gone over debugging that much, but you can print out what's going on at each step. There are tools to stop your for loop when something bad happens, an error or whatnot. The cons, though, is that these can become pretty complex quickly and then can become hard to read. The whole idea behind saving your work is messy, as you probably saw in And the homework we did in the first homework where you had to create an empty vector, do your work, save it, then print it out at the end. That can get complicated and clunky. And also, we'll see this later, it doesn't really fit that nicely inside other functions or pipelines, which what we're going to talk about later does and is important. So the function that kind of solves all of these cons is purrr map. So this idea that you map a function across elements of the list. I actually forgot why it's called purrr. The R's stand for something. I'll have to look that up. And so purrr map is a function. Map is a function inside purrr that lets us apply a function to each element of a list. It will always return a list, but the number of elements is the same as the list we input it with. So if you think about it, if you input a list of length 4, it runs the function on each of those 4 slots, returns the result, which is the length 4. So each slot of the return list will contain the output of that function applied to that element. And so kind of like how we applied print length here to each element and resulted in 4 things, we'll have a list of length 4 as our output. And the way to read map, and the kind of standard way of writing it is first argument is your list. The second argument is the function that you want to apply. So if I create a function of my own, I've created my own custom function called getFirstElement, which takes an input vector, returns the first element of a vector. So I'm assuming that the elements of the list are vectors. And I want to apply this to each of these 4 slots in my list. So this is easier if we know what our list looks like to create our function that we want to run. So I could do this the for loop way. And how would we do it that way? Just to show you, similar to what we did when we were iterating over a vector, we do need to create an empty list first, because that's going to hold all of our output. We're going to index, in this case, I'm indexing across 1 to the length of my list, which is 4. So 1 to 4. So index, the first time the for loop runs, index is equal to 1. The second time it's equal to 2, third is 3, and fourth is 4. And then, because that's the length, then it stops. And I'm printing out the index just so you can see this is the first step, this is the second step, third step, fourth step. And what I need to do is tell R to update my list. So the first time it runs, it adds the first element, so list index 1. And then I apply my function on my input list, my list index, which is this. So my list was my original list, list output is the new list I'm creating. So I run that function, get the first element of the vector, C, Morris, Julia. So I should get Morris in the first time, and then I should get Spiny, and then I should get Rover, and then I should get 10. And then at the end, list output will be length 4, and we can print it out. So I'm going to run this whole code chunk. Oh, wait, did I not call it? I didn't run that. I need to define my function first. I forgot to run this chunk. So I got the error, could not find function get first element. So that told me I either spelled my function wrong or I didn't define it, and I didn't define it. So I ran that up above. Now it should run. And so I can see this is from the printing 1, 2, 3, 4. It ran 4 times. Index was updated each time to be a number. And this is list output. This is the output from that. If I just run that by itself, that is the list of my result. So this is not nice looking, kind of complicated to have to create this empty list, update it each time, and then print it out. Purrr map is going to give us an easier way to do that. But before we get to purrr map, I want to show you another way to do this. And that is to actually write it out by hand. So I'm creating a new list by hand using the function list. And I'm applying get first element on my list 1. And then I apply it on my list 2 and my list 3, and then my list 4. So I'm applying my function on each slot of my list. That's exactly what I was doing up here with the for loop. Obviously, if I had 50 elements in our list, this would not scale well. I'd have to do this 50 times to write that out. And so really the idea behind automation is to do this automatically. And so if I ran this, I should get the exact same thing as above, a list of length 4, Morris, Spiny, Robertson. But I wanted to write this way because so you can see a little bit actually applying that function 4 times to each element and creating a list that has that output. So going back to purrr map, that's exactly what it's doing. It takes the list to process, it takes the function, you put it like this, you put the list first and then the function second. And so to do that exact same thing up above, all we have to say is map my list and then the name of the function. And I've saved it as new list. And we can see the output is almost the same. It's the same in that it has the same elements, but it's named. It has the original names. So my list was this. My list had these names. And now new list, which is applying that function, has the same names. So that's kind of a bonus. We get the names from above. And I didn't specify the argument names. I just used list, then function, because I know R will be able to tell that that's the order that the function arguments are in. But if we want to be specific, we would say .x equals my list, .f equals get first element. And you can actually see if we look at the documentation for map, those are the argument names. X is a list or vector, F is a function. It's almost always a function in our cases. So map is really handy, way simpler than anything else that I just did above, right? There's a lot less coding, kind of easier to read, understand what's going on. Okay, so I kind of want to get to the next, well, let's see. We'll try to get to the next challenge. So use map to return the length of each element in my list. So in this case, we want the list name first, then the function name. So my list was our list name, and we want to turn the length. So length is our function. That's as simple as it is. So my lengths, I'm calling that result my lengths, and I'm calling it out. And now we can see 2, 1, 3, 2. Simple stuff. We can get fancier. This is kind of a play example. In this case, we're mapping our list, our cupcakes. So we have 3 cupcakes. The function is frost. These little blobs are frosting our cupcakes. And then we can also see this third element, I guess, or argument, which is vanilla. And so just looking at this, it makes sense that vanilla is the type of frosting. So vanilla is actually an argument of frost. And so we've seen this kind of before when we used like summarize across, this idea that if something takes multiple arguments and include them at the end. So here's an example. If we have a list of vectors, numeric vectors, and I want to take the mean. So I want to take the mean of this, this, and then this. So 3 means I should get. So that's my list, and I map mean. But again, we have missing values. We see this all the time. We need to specify the na.rm equals true. So we can put the argument here. And we have na.rm equals true at the end of our map. So if we do that, then we end up with 3 actual values. And I think, what time is it? We've lost some people. Do you want to do breakout rooms, or do you want me to just go over this? Thumbs up or to breakout rooms, or no thumbs up to breakout rooms? There's only like 6 of you left, so maybe I will. What one is this? So this one's actually not that complicated, so maybe I'll just go over it with you for now, since it's getting late anyway. So this idea that we were using this function to pivot, to read in our data, pivot our data. So this is the function that we created up above. I just copied it down here. One change I made though here, and you'll see why in a minute, I switched the arguments. So I put sheet num first and file name. And that's because I want to apply this function to a list of sheet numbers. So if I want to apply a function over a list, that first argument should be the element that you're inputting. So I'll show you, I'm just going to collapse this. This is that function that reads in the data and pivots it. And so if I ran this, just to double check, define that function, and then ran that, I end up with, again, that pivoted data. This was from sheet num 2, so that's time point 1. So the idea behind this is to use that function, apply that function to a list of numbers. And so all you really have to do is first create your list. So we have 2 to 4 sheets 2 to 4. You can say, make this a list actually by hand. 2, 3, 4. If I look at what that it looks like I expect, it's a list of length 3, 2, 3, 4. You can actually use map on a vector, so this is sort of all superfluous, but data output. I'm going to use map on sheets, and then I'm going to use that function. What did I call it? Read and pivot. So what does this do? Oh, and I forgot my file name. What's it called again? This one. So I forgot to specify my file name. So I would do that here as an argument to my function. The first argument was sheet num, so it's going to put in a 2 and then a 3 and then a 4. And so if I run this and I look at the structure, actually down here I called it my out, so let's just call it my out. Structure, it's a list of length 3. The first is a tibble, the second is a tibble, and the third is a tibble. So what happened was it read the second sheet, which was time point 1. Then it read the third sheet, which was time point 3, 2. And then it read the fourth sheet, which is time point 3. And so now we have a list of length 3, each of the element tibbles, and we can actually name them. So I named them TP1, TP2, TP3. So now if we look at the structure, we can see that the names are here in front, right? And then if you remember from bind rows, we can pass a list, a named list. And then if we use this argument that ID equals time, it creates a new vector called time, or a new column called time, and uses the names of the list to specify where that data frame came from. So I ran this, and we should end up with the same exact data frame that we had up there where we bound the rows. So we have our long data because we have biomarker type. We have TP1 down here. Eventually, we'd end up with TP2, long data, TP2, and TP3 is all the way down there too. So this was the same as above, 448 rows. This is 448 rows and columns, same thing. So in that way, we simplified our code a little bit. We made a function that read it in and then pivoted it. We ran those functions on a list of length 3. And then it gave us a list of length 3. We named the list of the names we wanted to pull into that time column. Was the main reason I named them, so that I could add this column more easily. And then bind rows took that list as an argument. Similar to how we used across, you can create your functions inside map. I don't know that I would really recommend it. I'd probably just make my function name outside of map and then call it. but just so you can see, it's the same idea. So instead of using the named get first element function here, I'm creating, actually, I'll just put the argument names just so it's a little clearer. After the function argument, I'm putting the little tilde, and then I'm using .x as my argument name, and then I'm pulling out the first element of that input. So my list, you can see this. This was the original one, get first element, and this is just the .x version of get first element. And so it's the same exact result. So you could kind of get complicated and just like a shortcut and write your column, your function side map if you wanted. But I'd say I usually just create my function first, so it's a little clearer, a little easier to read. And you can see again this difference between using 1 bracket and 2 brackets. So in my get first element function, I used 1 bracket because I knew that everything up here was a vector. And so I just wanted to take the first element of my vector. But here's a list where one of the elements is a list. And so we had to be a little careful. So if I run this, what happens? It pulls out the first element, but because that third slot was a list, it pulled it out as a list. So this is a list inside here. If I use double brackets though, now it's pulled out 273, which was the first element, and it's pulled it out like a vector because that first element contained a vector. So playing around with double brackets versus single brackets, it doesn't matter here because everything is a vector. Everything inside that pet name list was a vector, but in this info list, address was a list. So this distinguishing between the 1 bracket and 2 brackets. Just so you can see, this was the 2 brackets. This is the 1 brackets. This is a list. This is 1 vector. So keep that in mind if you're using brackets for anything. Just a note to say that you can do this a tidyverse way and use the pipe if you want. So you would put the list first. Instead of a data frame, you'd have a list. Then you use a pipe, then you use map and put in the function. So not that that's any easier to read, but if you're doing a kind of a chain of operations with a bunch of pipes, sometimes that can be a little easier to do it that way, but you get the exact same answer. Okay, the last thing, yeah, we'll end a little early. The last thing, just to show you as kind of motivation for next time, because we're going to work a lot more with data frames. This is similar to the load, I forgot what it was called, load files. Oh yeah, load files function up above where I read in an Excel file and then use clean names. In this case, I'm creating a function that's called load CSV, which reads in the CSV file, then cleans the names, adds a column called source, which has the path name in it, and returns that data frame. One of the questions on the surveys a while back was, how would you read in 100 data frames or 100 CSVs into R? This is how you would do it. You would create a function that does what you want, making sure that it works for all 100 CSVs. But this is pretty general, so this should work for really anything. And then you would find out the name of your files. So there's a function called list.files. First thing I want to function before I forget. So list.files, which you tell it the name of a folder, in this case, inside my, let's look in here, data 2. I have 4 CSVs. And I use the argument full.names so that I get the full path. So here, what is that? That is the file name, the 4 file names. So I said that map will take a vector or a list, but I wanted to show you how to create a list out of a vector, and that is, you can just use the function as.lit. So I've created, I'll show you, this was a vector of paths. Now this is a list of paths for elements. You could name You could name them if you would. Kind of depends how you want to identify them. That's kind of up to you. It depends what your end goal is. But if I wanted to then load in those 4 data sets, I would say my names of my paths, my path names, and then apply that function. So here's my list of data. This is just the the message that R gives me. That's not that important right now. And then I could bind them because I know that these data types are all the same and look at that. But if they weren't all the same type, I could just look at those. It's gonna, structure's probably bad. Let's look at view. Too much information. So we have a list of 4 elements or slots, and each of them is telling me it's a tibble. It's telling me the rows and column names. So you could do that with your 100 CSVs and come up with a list and then put them together. If it makes sense to bind the rows, maybe it makes sense to bind the columns. Depends what kind of data you're reading in, but that is how we would do that. And so next week, we're going to talk more about using map on data frames and then how to kind of work with grouping variables and type specific maps, which return different kinds of objects. Here are some good readings on this stuff. I think if it's pretty new and probably to everyone, so I would recommend reading some of this in the textbooks, which have good examples. And that's all I have. Don't forget to turn in your attendance survey. Thanks for sticking around. Any questions before we go? All right. We'll have a good Wednesday.